Hello dear students, let's see this question of JEE Advanced 2019. So this is the setup of the question. No friction between the block and the horizontal surface. Pulley is ideal, string is ideal, everything is ideal, and this whole setup is release from rest, and at any given time, at any time, general time, the acceleration of this block is A1, the acceleration of this block is A2, acceleration of this block is A3, and the maximum extension of the spring is x0. And then we have to see which of the four options are correct. It is a multiple choice question, and we'll see one by one each option. So first thing that we can immediately see that if the acceleration of this block is A1, so is the acceleration of this pulley A1, and acceleration of these blocks are A2 and A3. And in this setup, if the string wrapped over the pulley is 180 degree, mean the two strings are parallel, then the acceleration of the pulley is the arithmetic mean of the acceleration of the both blocks. So then this option is straightforward, we can get. So we can write the acceleration of the pulley A1 is equal to A2 plus A3 by 2, and by 2 mean I can bring this 2 here. So that is actually A1 plus A2 equal to A2 plus A3. So then we can, this is A1 plus A1. So we can write A1 minus A2 is equal to A3 minus A1, and or we can write it A2 minus A1 is equal to A1 minus A3. So this option D is correct. Now for the rest of the option, first of all we have to find the maximum extension, and here in the B and C, in the option B, we have to find the speed of the block connected to spring, mean speed of this block at that extension, and at this extension we have to find the magnitude of acceleration of this block. So basically we have to find the speed and the acceleration of this block at certain moment of extension. So if I have to find only about the velocity and acceleration of this thing, I don't have to bother about the motion of these two blocks. I have to only bother about the motion of this block, and for the motion of this block, only thing that is sufficient is this tension. This tension is creating force, and that is the cause of the motion. So in place of this whole setup, I want to replace this pulley and the two masses to a single mass, such that tension on this string does not change. And if that does not change, so the motion of this block will not be affected. So whether you can put some different amount of masses such that still the tension is the same, so the motion of this 2m will not be affected. And for us, these A2, A3 are not important, and these masses are also not important, and I just want to replace this whole system, this pulley and the two masses, by a single mass. And this I've done in some of the previous videos, that we can replace this by a single mass, whether this pulley is stationary or moving up or moving down. And that mass, if that mass is, say, I am replacing this whole system by mass m0, and that the connection between m0 and, suppose this is m1 and this is m2, is 4 by m0 is equal to 1 by m1 plus 1 by m2, and I'll give you a very quick proof of that. So let me remove this part. So I'm claiming that I can replace this whole system, the pulley and the two masses, by a single mass m0, and the m0 will be given by 4 by m0 is equal to 1 by m1 plus 1 by m2, and this relation is valid even if this pulley is stationary or moving up with some acceleration or moving down with the acceleration. But here this pulley is going down, so I am taking a case in which this pulley is going down. So for that thing, what I can do, I can put this whole setup inside a lift of an acceleration going downward by an acceleration A. So suppose the tension and this equivalent also I will have to put on a lift with the same acceleration A going downward. And if the tension in this string is T, the pulley is massless, so tension here will be 2T. So here that 2T, same tension 2T, because I am replacing that thing. And if I draw the FBD here, so there will be weight m0 G and a pseudo force in the upward direction m0 A. So the resultant of the weight and the pseudo force will be m0 G minus A. So what we'll get? We'll get the 2T is equal to m naught G minus A. Now look to this situation. Suppose this was stationary, like a normal atwood pulley, then this tension would have been twice m1 m2 G upon m1 plus m2. Now because this whole setup is going downward, so the weight will be replaced by m1 G minus A, m2 G minus A. So this tension will become twice m1 m2 G minus A upon m1 plus m2. So this tension will become how much? Twice m1 m2 into G minus A divided by m1 plus m2. So this is the tension. So this 2T would become 4m1 m2 G minus A. So let me just equate these two. So if I equate these two, so I will get m naught G minus A is equal to 4m1 m2 into G minus A divide by m1 plus m2. G minus A gets cancelled, and you can bring it, simplify it, and you just simplify, you will get this result. So, and this I've got when this whole setup was going downward, but as I said, this result is valid even if the setup is stationary or going upward with some acceleration or going downward with some acceleration. So that result I'll use here. So I want to replace this whole setup by a single mass m naught, and that m naught will be here from this formula 4 by m naught. I can write that m1 plus m2 upon m1 m2. So that m naught will be 4 m1 m2 divided by m1 plus m2. And if we put these values, m1 is m, m2 is 2m, so that we will get 8m by 3, right? So I'm going to replace this whole mass by a single mass 8m by 3, and we'll make some more reductions. So for that I'll need to remove this. So I'm replacing this whole setup by another setup like this, and I'm further replacing this by another system, and I just want to make it a 1D problem. So if I look this whole thing, this weight and normal reaction will be balanced. For this whole system of 2m and 8m by 3, this tension, the string will be internal. There will be spring force from here, and there will be weight 8m by 3 G here. So I am further replacing the system by another system like this. And the last reduction, if I look this whole system together, again the tension in the string will be internal, so it would be better if I replace this whole two masses by a single mass, that is the sum of these two masses. So my final reduction is this situation, and basically the acceleration of this and this are the same because of the string constant. So whatever the resultant mass will be here after reduction of these two, their acceleration will be the same as this acceleration. Here this acceleration is a1 and this acceleration is a1, and this thing I have replaced in place of this. So now I am replacing these two again by a single mass, and the acceleration of that single mass will be same as the acceleration of this thing, and that will be our final reduction, and then we'll get our answer straightforward. This mu is equal to 2m plus 8m by 3, so that will be 14m by 3, and this f is equal to, f is 8 mg by 3. Initial velocity, everything was at rest, so initially at t is equal to 0, the t is equal to 0, this was at rest, and we have to find maximum extension of the spring and the acceleration velocity of this, actually 2m at certain instant. So now this is the problem of simple harmonic motion. If we talk about the time period, this constant force does not affect the time period, it only shifts the mean position. So let me first write the angular frequency of this simple harmonic oscillator. One thing, this mu is not the reduced mass, its symbol is that, but it is only the replacement of these two. I have replaced this 2 by a single mass, that is m. So the angular frequency of this system would be omega is equal to square root of k by mu, so that would be square root of k. Mu is 18m by 3, so 3k by 14m. And now the elongation. So if we look the motion of this block, this is at rest, so this is basically the extreme position, and then it will reach to the mean position, and at the mean position it will have the maximum velocity. So it will go to that side of the mean position, then it will reach to the other extreme point, momentary come to rest, then it will keep on moving like that. So it will reach to certain extension for so many times. So this is the extreme position, and suppose this is the mean position here, and then that is the other side of extreme position. So if this is the mean position or equilibrium position, so this is mu, this is the mean position, and that is the other side of the extreme position. So this is, it will come to again rest. Maximum extension will be here, because if it has a velocity it will go more. So basically we have to find the maximum extension. So if, and by the symmetry of the problem, if the maximum extension is x naught, so from here to here the extension will be x naught by 2. So this is the x naught by 2, so that will also be x naught by 2, so that its maximum extension is x naught. And this x naught by 2 is actually its amplitude. X naught by 2 is the amplitude. So let me calculate that maximum, maximum extension. So if we look to the mean position, so this force is a constant. So in the mean position there will be force F here. Mean position is also called the equilibrium position. So force F is there, and there will be a spring force, they will be balanced, so the acceleration is 0, so net force is 0. So to get, I think the job of this thing is done. I should remove this part. So here at the mean position or the equilibrium position, this force is F, and the spring force is K into extension, that is a K into x naught by 2. So kx naught by 2 is equal to F. So x naught is equal to 2F by K, and that is a direct formula also. So let me put these values. So 2F would be 16 mg by 3, and there is a K. So that is the maximum elongation, and the option A is saying that maximum elongation is 4 mg by K. So this is the incorrect option. And then it is saying that when the spring achieves an extension of x naught by 2 for the first time, here is the extension x naught by 2. So this position is the position of equilibrium. So at this position, the speed of the block, we know that in the simple harmonic motion, v is equal to, at any position displacement x from the equilibrium position, speed is equal to omega square root of a square minus x square, x the displacement from equilibrium position, and the position that is asking x naught by 2 extension is the mean position. So here x is 0, so there v is simply omega into a is the amplitude, and you can see that the amplitude here is nothing but x naught by 2. So the required answer for the part B will be simply omega a. Omega we calculated, that is square root of 3k by 14m, and multiply by the amplitude, which is x naught by 2. So x naught by 2, and we can put the value of x naught, so that would be square root of 3k by 14m, and let me take everything inside the square root. So that will be x naught square by 4 inside the square root, so 4 here, and 16 square m square g square, and by 4 we had already written, and there will be k square. And on simplification, we are not going to get this answer also. So this option is also an incorrect option. And then we have to find in the option C, extension x naught by 4, the magnitude of acceleration of block connected to spring in this block, and this block acceleration will be the same as the acceleration of this block that we discussed. So when the elongation is x naught by 4, so elongation x naught by 4, this was a natural length position, so elongation x naught by 4 mean in between these two. So here is the, somewhere here is the elongation x naught by 4. And I'll use another result of simple harmonic motion. Acceleration at any point in simple harmonic motion is minus omega square x, and that is the main thing. If we have to prove the motion is SHM, we have to arrive to this result only, this expression only then we can say the motion is SHM. Here x is the displacement from the mean position. So if I talk about the magnitude of acceleration, so that magnitude of acceleration will be omega square into magnitude of displacement from the equilibrium position. This is the equilibrium position, and this is the extension x naught by 4, this is x naught by 2. So displacement from the equilibrium position or the mean position is also x naught by 4. So when the elongation is x naught by 4, displacement from the mean or equilibrium position is also x naught by 4, because x naught by 2 is the amplitude. So put it here, omega square is equal to 3k by 14m, and that x is x naught by 4, and put the value of elongation that we obtained. The elongation we obtained is this, so x naught by 4 is 4 mg divided by 3k. So that 3k will get cancelled, so we will get 2g by 7, and that is also not this answer. So this option is also incorrect. So only thing we remain, the correct answer is option D, and that is our answer.